So let me first talk about Spins. Spins is a wellness-focused technology company. We partner with brands and retailers across North America to drive the industry and the world to a more sustainable future. A core component of our business is collecting retailer sales data, and we use this data to get new, innovative, better for products on the shelves of our retail partners and brand partners. Spins has been around for over 25 years, and we've continually innovated in the natural and CPG space to stay on top of emerging trends, such as the organic trend that hit years back, keto trend, specialty pet is popular now and kind of taken off. On the tech side, we've made heavy investments into Google Cloud. We're actually, for better or worse, one of Google Cloud's largest client, actually I think the largest client for their BigQuery platform, which is one of their data stores. So we do have a lot of data. We also built out a data science team about 5 years ago, and it's been growing ever since. In 2021, we got some private equity funding from a company called Georgian, and I'll talk about them a little bit. So as I mentioned, Georgian's a private equity company. They invest in growth stage AI companies like Spins. They have a dedicated research and development team, and my data science team engaged with their R&D team. And the result of this presentation has really been a collaboration of both teams, so I just wanted to give them a shout out on this slide. Okay, so what is the problem that I'm going to talk to you guys about today? I'm going to start at a very high level describing the problem and then really narrow that down to a specific machine learning problem and how we solve that at Spins. At Spins, we receive product data from over 600 plus retailers in North America. And we take this data and we combine it into one industry-leading product database. As you can imagine, we get data from 600 different retailers, and there's a lot of challenges that comes along with this. So we get data in multiple formats. Data can be missing, data can be incomplete. Entities are represented in different ways from retailer to retailer, file to file. Even within the same file, we have different entity representations. Data can be incorrect, outdated, and if we get it late. So lots of different things that we have to handle as we process this data. What we do at Spins, we take all this data, combine it into a simple normalized format that's complete, and clean, reliable, auditable, up-to-date, coherent, and consistent. And I want to highlight in orange here this reliable principle. I'll refer back to this a couple times during the talk. This is super important. We need to keep our data as reliable as possible because Spins sells data. So this is a key principle to keep in mind throughout the presentation. So let's take a closer look at what we have inside of our product library database. So here I have just a generic product. You can think of this as any product on the shelf of a grocery store, like a bag of chips, a bag of crackers, cookies, water, whatever. And we have over 200 attributes for over 3 million products. This is growing every day. Some of the attributes we have are product fact, things like the size, the brand, what part of the grocery store that item belongs in, the subcategory, the packaging type. We have allergen and sensitivity information, so if you're a gluten-free shopper, we've got you covered. We have that attribute in our database. We have sustainability attributes like non-GMO, health and wellness attributes, so if folks are looking for certain functional ingredients as part of their diet, we have that as well. Lifestyles and diets. So for the paleo shopper, the vegan shopper, we have those as well. And lastly, we have clean ingredients, so like aluminum-free, things like that. So we have a lot of different attributes. Over 200 right now. This is growing every day. As you can imagine, it's a lot of work to maintain this database. At Spins, we have a dedicated product intelligence team, and it is their job to keep this data set up to date. So that team responds, they look at our sales data. If they see a new item hitting the market. It's their job to get that item into our database as fast as possible. And that is where the data science team came in, my team. So we partnered with product intelligence to help them increase the velocity of new products into the database, keeping in mind the reliability and accuracy that I mentioned earlier. We need to make sure whatever is being entered into this database is as accurate as possible. All right, narrowing down kind of the scope of the problem, let's talk about product intelligence at Spins. So I know this is a computer vision, as part of the computer vision track. We do computer vision work at Spins. I'm actually going to talk mainly about natural language processing, so I'm sorry to disappoint anyone who's here for computer vision. But this is a typical item that we would get at Spins as in one of our image pipelines. You can see Nature Valley, soft baked oatmeal squares. And how do we define a product like this in Spins in terms of data? So we define a product based on its attributes. So as you guys are looking at this product on the screen, you can tell with your human eyes what the brand is, what the subcategory is. It's a shelf-stable granola bar. There's 6 bars in that package. The unit of measure is 6 ounces. The unit size, total units in the package is 7.44. And we do have a computer vision pipeline that does this at Spins. However, that's not the focus of my talk today. So I'm going to be focusing on the product descriptions that we receive in retailer sales files. So we want to derive these same attributes that you see in the image using only textual product description data. And by product description data, I mean what's below here. So we also receive the same type of data about Nature Valley oatmeal squares, but we receive the description through sales data. So it was Nature Valley soft baked oatmeal squares. And that is where the pre-trained language models come into play. All right, narrowing the scope even farther to a specific machine learning problem. From this text below, we want to determine the brand, and that's what we're going to be talking about for the rest of this talk. So brand identification. We want to identify the brand entity from a retailer product description. So here to the left, this is an example data that we might receive from a retailer. We have a UPC code, and we have product descriptions. The product descriptions are featured to our model, inputs to our model. To the right, the brand column right here, this is what we're trying to predict. So we approach this as a traditional classification problem. And as you might have noticed, looking at some of this data here, there's a lot of challenges that come with determining brand from some of those product descriptions. There's not a lot of information there. Product descriptions can have the brand embedded within the description themselves. So, if the brand here would be Pillsbury, sometimes we get a partial branding. You can see that here, Great Harvest, it's missing some letters. Sometimes you can get an abbreviation. NEBC, this stands for New England Brewing Company. And then lastly, sometimes we get no indication at all of any brand in the textual data, such as this neem oil example. And as I mentioned, we partner with over 600 retailers. So for one singular product, we might get hundreds and hundreds and hundreds of descriptions. So for that example I showed you, that package of Natural Valley soft baked oatmeal squares, we might get any of these descriptions below. Sometimes we just get a UPC code, which isn't very helpful, but fun example I like to throw on slides. What makes this problem even more challenging is Spins has 86,000 brands in our database. And since we approach this as a classification problem, that's just an enormous output space for that type of task. And over half of the data comes from the top 1,000 brands. So how do we initially tackle this problem? Oh, there it is. So we initially tackled this problem by going really simple. We developed some rules and heuristics to try to extract from text data. So we employed different rules such as string matching. We did some thresholding percentages, and we applied these rules in a tree-based method, as shown to the right there. And how did that perform? We actually got 77% accuracy on this, which I thought was pretty solid as a first pass. But there were many drawbacks that came with this approach, such as multiple brands can have the same product description. String matching isn't perfect. We got a lot of false positives out of string matching. Choosing thresholds that we were looking at is tricky. There's always a trade-off when you're choosing a threshold, as data scientists sitting here know. And the last two are kind of the critical drawbacks in my mind with this methodology. Oh man, my slides all messed up. And those two critical drawbacks are, the first one is predictions are not probabilistic. So going back to that reliability piece, when we got a prediction out of this rule-based model, we never knew if it was a good prediction or a bad prediction. There was no probability score output from a rule-based model. This is a problem for us because we want to be as reliable as possible. When we make a prediction, we need to know if it's good or bad. If it's a good prediction, we can have some sort of automation in the system. And we couldn't get that from the rule-based model. The last piece is that the rule-based model was actually hard to maintain and scale. So we kind of handcrafted some of these rules. Data shifts over time. We see our data shift over time seasonally. And we didn't want to dedicate data scientists and analysts to having to go back and engineer more rules to make the system sustainable. So we looked to machine learning to help us out. And sorry, the slide isn't perfect, but does anyone know this little guy, this happy guy? Yeah, Hugging Face. Okay, good. Awesome. So we use Hugging Face. And we trained a BERT transform model. We took 80% of our item description data, product description data, and fine-tuned the BERT transform model. We hoped that using a large language model like BERT might help some of the edge cases that the rule-based model wasn't picking up. Some of the syntactic variation that we were seeing in those item descriptions. So let's see how the BERT model performed. So we actually had 55% accuracy with the BERT model. So it underperformed comparatively to the rule-based model. So at first we were a little disappointed in this. Some of the drawbacks were we saw a 22% decrease in accuracy. That's kind of the glaringly obvious one. We also saw that brands with lower samples were almost never correctly predicted. The rule-based model was much better at predicting brand values, kind of that long tail distribution that we had. So those were two drawbacks. But let's talk about some of the benefits of using some machine learning here. All right, so some of the key benefits, and I kind of teed this up a couple slides ago. We knew which predictions were reliable due to the probabilistic nature of the BERT model. So we got a prediction, we got the brand, and we got a probability score. And for us, this unlocks automation. So if we got a prediction with high confidence or high probability, we can automate that. We can automatically write that attribute to our product database and move on. If we get a low probability score, we can send that textual description to a human on the product intelligence team so they can review it. So this was kind of critical for us, a critical feature that we needed to move forward. And lastly, the transform model is more scalable. We can retrain it whenever we want. We can set a gain. We can click a button in Airflow and just retrain it whenever we need to. So it's much more sustainable long term than having an analyst go back and kind of revamp rules. All right, let's see. Okay, and ultimately, we ended up putting the BERT model into production for those two main reasons that I mentioned. Man, these slides are struggling, sorry, apologize. All right, I got a couple minutes left. I want to touch upon MLOps since this is important and a piece that I care about a lot. So this is a high-level overview of how we productionize the BERT transformer model. It's broken down into 3 sections. We have model training, model serving, and then the usability by the PI team over here to the right. Focusing in on model training. Model training is kicked off when new data is available. So we have an external event. When we have new data, we kick off retraining. So this is automated. This is done by a message queue. This triggers our Airflow pipeline, and this is where all the model training happens. So we write our training data, we train our model using GPU, then we save that model to the model registry. Last step is model assessment. We assess the latest trained model against previous models that we've trained. If it passes our assessment criteria, we then promote that model into model serving. So let's talk about model serving. For model serving, we package the model and all its dependencies up into a Docker container, and we run that container, it's an API, on Google Cloud Run, which is a great tool. If anyone's used it, I would recommend checking it out if you're looking for hosting an API. And the REST API is great. It can be accessed pretty much by any language. So that was a huge win for us. Other tech teams can easily hit this API and get data back. It also has the ability to load in a model inside the model registry. So we can do shadow testing and compare past models against current models, things like that. The last piece, when we get new product descriptions that are not already in our database, the product intelligence team can send those to our REST API, and in return, they get the brand as well as the probability. And the product intelligence team can then use that information wherever they want. They can automate the brand attribute value, the brand entity value, and automatically write that into the database. They can use it for augmentation. They can recommend different brands to the product researcher, or they could just ignore our predictions if you don't have a good prediction at all. So that is the use. All right, I got 1 minute. I'll touch on impact. So what is the impact of all this for spins? We can automate with very high confidence 30% of brand identification. And this helps us reduce time to add new items to our database, as well as cost. So, humans are very important assets at spins. They can spend their time doing other tasks that the computers can't figure out. Spin sells data as a business. So if we have product information about every single item on the shelves of the retailers that we work with, that's good for us. Retailers will continue working with spins and we'll get new business. And the last point is this is a differentiator for spins in terms of us versus some of our competitors using some of the best in class AI.